Hello students, welcome to Lecture 5, Swell Basics. So what we have learned so far included all these 5 components: contours and contour rules, landform types and contour signatures, graphical standards and conventions, slope formula and calculations. And last week we started grading level terraces with 3 different kinds of methods. So the purpose of that was mainly to create level areas for human activity. And today's lecture is intended to help you understand how to keep these areas protected from water. We'll cover 3 topics: basic swell guidelines, what key components does a swell have, how should we calculate swells? There are 5 important points about swells that you need to remember. The first is that the only reason to have a swell is to protect structures, that is anything man-made. Protect structures from water flows. Think of swells as protector modes. Things that need protection include any building, sidewalks and paved areas, roadways, and parking lots. Soft surfaces such as sports fields and general open recreational areas also need to be protected from runoff from adjacent areas. And as we learned in previous classes, the swell signature is a set of V or U-shaped contours with the closed end pointing in the uphill direction. And this contour signature collects water. And in the plan view, the contour pattern you see here is typical of a swell around a house. They often occur in pairs, although they don't necessarily have to. And they may be more or less symmetrical depending on the existing landform, the location of the high point, and orientation of the structure to the landform. We'll talk more about that in future slides. You can see how this pattern is designed to take the sheet flow coming down the hill, direct the water around the building on the site, and then gradually blend back into a sheet flow. So, without features like swells to protect buildings or other structures, serious consequences can happen, right? Here are just a few examples of what could happen if water is not appropriately managed around infrastructure. Basements can be flooded, roadways can collapse. In more serious cases, sinkholes can form and cause property damage at the very least, lawsuits, and even death. And all this is to say that understanding site drainage and effectively protecting structures such as buildings, retaining walls, and roadways from the concentration of water flows is an important responsibility of ours. Now, the second important point about swell is that swell will always be on the high side of a structure because its purpose is to divert uphill drainage around the structure. As we discussed on point 1, a swell cuts off the drainage from uphill, as shown by the blue arrows here, and diverts it around a structure before returning to the original flow direction. And you can see the swell carved into the hillside on the section on this slide. Now, the third point is that the surface of the ground immediately adjacent to the structure must slope away. They must always drain away from the structures, right? And this is called positive drainage. And we will mention the term of positive drainage numerous times throughout the semester. And this section here shows how the water is diverted from the structure. It drains positively away from the building or structure. Notice that this includes all sides of the structure, even those that don't have a swell. And we'll give you grading standards for these other areas and discuss how to grade them properly as we move through the semester. But the key thing here is all the surface of the ground immediately adjacent to the structure must slope away. Otherwise, water will enter your house, right?
Now the fourth point, the location of the swell high point is important. The high point of the swell in our class is often referred to HPS. You can see here how the high point and the area around it form a saddle type of landform, as we have discussed earlier. This saddle allows water from the slope and the parking lot, the structure we're trying to protect, to drain toward the high point. Once the water reaches the high point, it moves perpendicular along the swell center line as it drains around the perimeter of the parking lot. Also notice that there is another swell at the top of the slope to keep water from the rest of the watershed from even reaching the swell at the bottom of the slope. This approach reduces the need for a large swell adjacent to the parking area by diverting most of the uphill water around the embankment. And generally speaking, locating the HPS about midway along the width of the structure creates a symmetrical pair of swells and balances the grading on both sides of the structure. But this can and will vary from situation to situation. Now the fifth point. Swells are often subtle. Don't make them overly deep or exaggerated. In most cases, swells will not be that deep or obvious. In some cases, swells won't be obvious until they have flowing water in them. When swells become deep, you'll start to have more restrictions on what you could do on that land, right? Also, steep side slopes encourages erosion and are more difficult to maintain. This example is from the Princess Diana Fountain in London, a landform-based fountain that we introduced in our first class. As you can see here, the swell doesn't really affect people's activities until it starts to be filled in with water. Here is another example of a swell. Can you see which way the water is going? It's pretty hard, right? However, you could see the fall of the driveway in the background. So in this case, the swell here is moving downhill from right to left. Here is another example from Finland. You can see the swell on the left side between the building and the bike path to protect both structures. Next, let's talk about key components of swells. They're all very important. They work together to create a closed system. You can't change one part without changing the other parts. So, to properly describe and construct a swell, you must have all of these shown on the drawing. The first one is the swell center line. It defines the path of the swell, the direction of the water flow, and is used to calculate horizontal distances. The centerline slope defines the relative flatness or stiffness of the swell and may change at intermediate points along the swell if necessary. That is to say, the swell center line does not have to be at a constant slope. So the center line is represented by a line with a single dash, which is a conventional symbol representing the center line of anything. Second, the high point of the swell. This is the highest point along the swell center line and occurs at the intersection of two axes of the saddle. If you remember this figure from previous slide, the HPS is the lowest point for the blue flow, but the highest point for the yellow flow. The third component is the low point of the swell. That is the lowest point along the swell center line and represents the point where the swell ends and it's blended back to sheet flow. Sometimes the water can be collected in a drain at the low point, but that won't be a situation in this class because our focus is on using natural systems to manage water wherever we can. So an important point here about the LPS is that it is the location where the swell ends, returning to natural grade, meaning the elevation of an LPS is what the original elevation of that location is. It also means when contractors build the swell, the earth moving activities stop here. Now the fourth component, the contour spacing. The contours need to be spaced at the correct distances to represent the slope of the center line. Now, the high point and the low point are critical parts because, as we discussed last week, they are the points that will be staked out in the field and used to create the swells. The contours matter less than the spots. They serve as a reference and an indispensable tool for you as a designer, but to the contractors, they aren't the most important information on a grading plan. And all of these key components must agree with each other mathematically. What does that mean? Here are just a few examples. The differences between the high point and the low point must agree with the slope percentage of the center line. The spacing between the high point or the low point and the closest contour should agree with the slope center line percentage. And the spacing of 1 foot contours definitely should agree with the centerline slope, right? So you may calculate and locate the contours from one end, but you always need to check the remainder to be sure your math agrees with your graphics. This is important because the graphics are a check of the math, not just because we want you to draw accurately. Using proportions is a great way to do a quick check, even without a scale or a calculator or in CAD. Here is just a quick example where if you are designing a constant slope for the swell center line, the contour spacing must be uniform or consistent as well. In this example instead, you can see that there appears to be a change in spacing along the center line of the right slope. The green spacing seems to be longer than the other two, right? This indicates that there is a slope change somewhere along that center line, and you must indicate clearly where that slope change occurs using a spot elevation, like this one. By placing this spot along the center line, there are now two slopes on the swell, one from the HPS to the spot elevation of 10.50 and another from the spot of 10.50 to the LPS, which isn't visible here, by the way. This principle applies to all surfaces and slopes, not just swells. Well, whenever there is a slope change, an additional spot elevation is required to indicate where exactly that change occurs. As we have been saying, the spot elevations control the construction, not the contours. In your professional careers, contours will probably come to mean less as automated construction methods take over manual methods. GPS and laser control construction equipment, such as bulldozers, graders, and scrapers, are already in service and work from 3D landform data that can control the tilt and depth of a cut or fill and provide real-time location information for the operator who just has to control speed. With that said, contours do matter to us and to you. They are important tools to visualize the intended landform and provide a way to be sure that the numbers can actually create the landform you have in your mind.
Next, let's talk about the side slopes of a swell. The center line is important, but it is only part of the picture. The side slopes are also important. They can be flat, as in the example on the left for a swell, or they can be steep, as in the example of the ditch on the right. Side slopes may vary depending on the situation, depending on what's the depth of the swell that you desire, or it will depend on the context. So what is the land use adjacent to that swell, right? So the slopes on the two sides are typically the same, but they don't necessarily have to be.
Over the years, we have found that the concept of the depth of the swell tends to be easy to understand in the section view, right? Essentially, the depth is the elevation difference between the top of the bank and the invert along the center line. But it's fairly difficult to understand what depth means on a plan view, and we'll explain that in more detail with the next slide. But before we move on to the next slide, I just want to point out that from the contour patterns of swell versus ditch shown on the plans here, you can see contour spacing of the ditch is much closer than those of the swell on the sides, right? Although their center line slope can be exactly the same as indicated by the same contour spacing here. Next, we'll be looking at three swells that have the same percentage slope on the center line, but will have different depth and see how this affects the contour signatures. Let's use the middle one with a depth of 1 foot as an example to further explain depths. Note that here all the numbers represent elevations. So, let's start from scratch. The question here is that given a known constant centerline slope of 3%, what does the contour signature looks like for this swell? In this simple example, we also ask you to make the side slopes consistent as well, which means if we were to construct a cross-section for the swell, no matter where we locate the cross-section cut line, the shape of the section remains the same. Okay, now let's just start to draw the cross-section from this location where the elevation at the center line is 9. First, we find the elevation at the center line, and then because the predetermined depth of the swell is 1 foot, the elevation here at the top of the side slope is 10 feet. So here is our cross section. And now you know that our 10-foot contour should connect in this way. And because this is a swell with uniform side slopes, you could simply copy the 10-foot contour to find the locations of the 9-foot and 8-foot contours. But you could also follow the same process to find where 9-foot and 8-foot elevations are on the sides and then connect the dots. You may have noticed that the contour shape that I just drew is a little different from the example directly from the book. That was a little intentional. I just want to point out here, for your exercise, we're less concerned about the exact shape of your contours. Instead, you want to make sure that these key connection points for the contours are correct, both their locations and their elevations. Okay? Now let's get back to the busy figure with the 3 swells and look at the other 2 that have different depths using the same principle. Okay? We'll start with the upper one that is 6-inch deep. And we are assuming there's no contour lines as of now on the map. We're still trying to find where the contours should be for the 6 inches deep swell. Okay, the depth is 6 inches, which is 0.5 feet, which means the elevation differences between the point A on the side and the point B on the center line is 0.5 feet, right? And in order to find where the 10-foot contour connects on the side, we need to find where the center line spot B equals to 10 minus 0.5. That is 9.5 feet. So all we got to do is to find the midpoint between the 9 and 10 contours along the center line and then find the corresponding spot A on the side across the swell. Then we connect A with the original spot that is at the 10-foot elevation along the center line. There we go. We got the 10-foot contour for the swell. Okay, and you can copy the 10-foot contour to form the 9 and 8 contour as we discussed on the previous slide. The same process goes for the swell with the depth of 18 inches, which is 1.5 foot. So for instance, in order to find where 11 connects on the side, we got to find where the centerline spot B equals to 11 minus 1.5. That is 9.5 feet. So in summary, the contour patterns of swells with the same centerline slope are different if the depth of the swells are different. Okay? Okay, on to the next slide. With these graphics, I want to explain that the depth of the swell can also be determined by looking at the proportional distance between the contours along the center line and the edge. Now let's look at the graphics. We'll start with the 6-inch deep swell on the top again. The width of this gray box is 1 contour spacing for the slope along the center line, right? And if you look at the location of spot A, that is the spot at the 10 feet elevation on the edge, is exactly at the half contour spacing from the spot that's at 10 feet elevation on the center line. I know that is a mouthful, but you get the idea. And why is that? So in terms of elevation, A and A1 should be the same, right? Because they're both at the 10-foot elevation. And if the elevation difference between spot A and spot B is 0.5 feet, that's the depth of the swell, right? Then the difference between A1 and B is also half foot, which means the horizontal distance between A1 and B is 0.5 contour spacing. Does that make sense? This exact principle applies to the other swells too. So for the 1-foot deep swell, this distance is exactly 1 contour spacing. And for the one at the bottom, which is 1.5 feet deep, the distance is 1.5 contour spacing. Now onto the calculations of the swells. We're certainly not the first ones to design swells, so there are standards for how to design them and how to design other types of surfaces. Now this is a table that is similar to the slope formula. It is worth printing out and keeping handy alongside with you because you will be designing all kinds of different surfaces throughout the semester and you will be needing to refer to the desirable range column of this table. Okay? And notice that the desirable range is the one that we should use in our design because the extreme ranges, we should not use them unless absolutely necessary. Now for the swell exercise, these are the 3 slope ranges that you need to know. The first one is the grassed swells, and that is referring to the centerline slope of a swell. And the desirable range is 2 to 10%. Now think about why do we not want to have a swell that is less than 2% along the centerline? Because with possible construction error and future sedimentation, the centerline slope might even drop below 2%, right? And in that case, the slope would not drain well, and you would not want standing water in your swell. Because remember, the reason for a swell to exist is to direct water away from your structure. Okay? And why don't we want to go steeper than 10% on a grass swell? The steeper the centerline gets, the faster the water moves through the swell, right? And then if you get fast moving water, what do you get next? Potential erosion, right? And it's very hard to maintain as well if your slope gets above 10%. We also need to know the slope ranges for grassed and planted banks because they apply to the side slope of our swells. For the grassed banks, the desirable range is up to 33%, which is corresponding to a 3 to 1 slope, and for the planted ones, the desirable range is up to 50%, equivalent to a 2 to 1 slope. And why is grassed banks lower than the planted ones? Because they have to be mowed. Okay? In order to allow them to be mowed, you need to have a lower slope than the planted ones. Moving forward with the calculation, and you all know that there's only one key formula, right? By now, I'm confident that everyone is familiar with the formula, so we'll move forward to give you some examples. So when asked to calculate a parameter for a swell, you always ask, what do I already know? Which variables in the formula do I already know? And what do I need to find out or calculate? So in this first example, the known parameters are HPS and LPS, and you could measure the H from the site plan. And we are to find out the centerline slope. And in this case, you would use the formula of S equals to V over H multiplied by 100, right? And in this second example, you know HPS or LPS, only one of them. You know the centerline slope, you know the H from measuring the plan, and the question is, what's the other spot elevation? So suppose that we know LPS here from the section. What's the HPS? Here you would use V equals to H multiplied by G to find out the vertical change from the HPS to the LPS, and then you add V to the LPS to get HPS, right? So in this last example, you're given centerline slope percentage, the HPS elevation, and you are to find out the location of a whole number contour. So where is this contour located on the plan? This is essentially asking you to find out an H, right? So you could use the whole number contour elevation to find out the vertical change from that contour to your HPS. And with that, you could calculate H by V over H. Okay, then measure that distance on the plan, then you have the location of that whole number contour. Now let's run through the process of calculating the various parts of a swell from scratch, as you will be doing the same for the exercise. So example A is for a 6-inch deep swell. What we know here is the centerline elevations and centerline slope. Also, we do know the width of the swell is 25 feet. Okay, what we need to do here is to plot the contours for the swell and also find out what the side slope of the swell is. So what to do as the first step? Very similar to the slides when we explained what the depth of the swell is. The first thing we do to mark and locate the 0.5 feet elevations on the center line. Okay? And the next thing we do is to use the swell depth, which is 6 inches, 0.5 feet, to find the elevation at the edges. In this case, the 8 and the 7 on the edges. Next, we connect the dots to draw the contours. One last thing that we need to find out is the side slope of the swell. Let's borrow the cross section that we constructed before in previous slide. So this is to find out the side slope indicated by the red arrow. And because it's a slope, we know that the formula to use is S equals to V over H multiplied by 100, right? But what is V and what is H? V in this case is the depth of the swell, which is 0.5 feet, right? And H here is half of the width of the swell. So we enter those values into the formula, we get the slope equals to 0.5 over 12.5 multiplied by 100. And the final calculation gets 4% for the side slope. For the next example B, we're given different parameters. Same as before, we're given the centerline elevations and its slope. But this time, we are given the side slope of the swell, which is 8%. The width of the swell stays the same as 25 feet. Now the task is to plot the contours and to determine the depth of the swell. So the first step for us is to use the side slope of 8% to calculate the vertical change in elevation from the center to the edge, as indicated by the arrow here. So what is the elevation for this spot on the edge? We know we're calculating V. So the equation to use here is V equals to H multiplied by G. H equals to half of the swell width, and G equals to 8% divided by 100. So that means V equals to 1 foot, and this V is the difference between the spot on the edge and the 7 elevation along the center line. So the swell depth is exactly 1 foot. And now what's left is to plot the contours by connecting the dots, right? Simply connecting the 8-foot elevation spot on the edge with that on the center line to form the 8 contour. And you can copy the 8 contour to the 7 elevation spot on the center line to form the 7 contour. Next, we'll quickly go through another 2 example, which is really very similar to A and B, just with different numbers. So example C here, we have elevations along the center line and its slope. We have the width of the swell staying at 25 feet, and we have the depth of the swell as 18 inches, 1.5 feet. And the task is to plot the contours and find the side slopes. So again, our first step is to locate and label the 0.5 feet elevations on the center line. And next, we use the swell depth of 1.5 feet to find the elevations at the edges. So those are the 8 and 9-foot elevations on the edges. And the third step would be connecting the dots, right? Again, to find out the side slope of our swell, we use the slope equals to V over H multiplied by 100. And in this case, V equals to the depth of the swell, which is 1.5 feet. H equals to half of the swell width. Now we get a side slope of 12%. Last example, this one is very similar to example B, just with a different side slope number. So in this case, again, we have the elevations along the center line. The width of the swell stays at 25 feet, and the task is to determine the swell depth and plot the contours. So the 12% side slope, first we use that to calculate the vertical change in elevation from the center to the edge, and then we use V equals to H multiplied by G. H in this case again is half of the width, 12.5 feet, and G is 12% divided by 100, so 0.12. Now V equals to 1.5 feet, so that means the depth of the swell here is 18 inches. And the last step is just to connect the dots like before, right?
So for the last slide, I just want to bring together these 2 examples. They totally agree with each other, right? They are essentially the same swell. We were just given different variables each time and asked to calculate others. But the key here is to understand which formula to use for which variable and what V or S or H refer to when it comes to centerline slope versus side slope. That's all for this lecture. Thank you all for listening, and see you in class.